Good morning. Welcome to the International Space Station Flight Control Room. As we mentioned earlier in the hour, this week the crew surpassed a record they had previously set on number of hours that they spent working on science this week. And here to tell us a little bit about that, we have Vic Cooley, who is the lead increment scientist for this expedition. So thank you so much for joining us, Vic.
Thanks, Brandy. It's a pleasure to be here.
We're glad to have you. Well, so first of all, why don't you tell us a little bit about what a lead increment scientist is? What does that mean?
Well, I'm ahead of a team that's an international team that consists of NASA scientists, but also partner scientists from our partners, JAXA, the Japanese Space Agency, the European Space Agency, and also the Canadian Space Agency.
So you get them all rounded up on
We
what
meet
scientific?
weekly, and our primary objective or our routine product is every week we put out a list of priorities that for the next 4 weeks to indicate which science sessions should be higher priority than others. As our audience is probably aware, the tightest resource, the one that often limits how much science we can do on orbit, is crew time. So that's the resource we're most often focused on. But other times it's bandwidth or upmass or some other resource that the investigations need.
Okay. And so when you say you set priorities, that means you decide which experiments are going to be the priorities, or is that the way to describe it?
Yes, and it's probably more accurate to say we decide which sessions or which runs of which experiments take priority in a given week.
Okay.
A lot of our experiments are on the crew members themselves, and those have requirements that are defined by how long the crew member has been on orbit. So, for example, we'll collect blood at flight day 15 and at flight day 30, and then again at flight day 45. And the intervals start to increase as the crew member stays there longer and longer, such that the last interval could be as big as 60 days, whereas the first interval is only 15 days.
Okay.
So those are pretty well tightly defined windows at which we need to conduct those blood collection sessions. Other experiments in the physical sciences area, and I'll talk about some of those later today, don't have tightly defined timing requirements when the sessions have to occur. However, some of those experiments do have specimens or samples which can be shelf life limited because they would coagulate or something like that if they're there for too long. So we have to take those kind of considerations into mind. We also have to consider when is the return flight for a particular set of samples. And so a lot of different considerations go into deciding what are the priorities for a given week.
It sounds like a pretty difficult scheduling question to get through.
Well, there's lots of teams involved that actually do the scheduling after we set the priorities. But it's very enjoyable to work with this international team and learn about all the science all the wonderful science that we're doing on the space station in almost any discipline that you can imagine.
I bet, yeah. Well, I think the record that we're setting this week, I guess at the end of today, will be 67 hours of time spent on science.
That's correct. That's 67 hours this week by our three USOS crew members, Kevin Ford, Tom Marshburn, and Chris Hatfield of the Canadian Space Agency.
And so that doesn't even count the Russian experiments that the Russian crew members are doing on the other end of the space station.
That's correct. It does not.
Okay, well, 67 hours, that's pretty good. I think it just is a little over our last record was 66.
I was thinking 65, but
Okay.
it's very close. But we're happy to set the record.
I bet that's great. So what are some of the things they've been working on this week?
Well, today I've picked 4 experiments that there's kind of a theme involved. They're all in the fluid physics area. And actually, we could call this Fluid Physics Week because I know 2 earlier interviews you've had this week with Dr. Eric First of the InSpace experiment and Dr. Mark Weislogel of Portland State University for the CFE or capillary flow experiment. They have both been interviewed on this particular program this hour on previous days this week. I'll talk a little bit about those, trying not to duplicate things they've said, but I'll also talk about 2 partner experiments from the European Space Agency, the GeoFlow experiment, and from the Japanese Space Agency, the Marangoni experiment.
I think this is a video of GeoFlow.
Yes, this is a GeoFlow video. First of all, the name is very appropriate because it examines the flow in the center of our Earth, so GeoFlow. In this case, we have a set of hardware on board that it's 2 concentric spheres with oil in between those spheres, and these spheres aren't that big. The outer sphere is about the size of a volleyball, and the inner sphere is about the size of a hardball baseball. And in between those two concentric spheres is this silicon oil. Now, there's a voltage difference between the inner sphere and the outer sphere, and that produces a force field much like our gravity field, which is, centered at the center of the Earth. In this model of the Earth, that gravity field is centered at the center of the inner sphere or the baseball sphere. So it's not, you could say, well, we're going to space to eliminate gravity, but yet you want gravity. Well, this is a miniature gravity model in that it's centered at the center of that inner sphere. You can also apply a temperature difference, which creates flow inside between those concentric spheres. And the model that you saw previously in the video was an interferometric imaging of that flow. You can see those inner cells simulating the molten flow of the mantle of the Earth. This is important to understand the flow in the mantle of the Earth, so that we can understand volcano and earthquake dynamics more and what causes them, and perhaps improve our capabilities of predicting those phenomena. But it also has applications for spherical ball bearings, for heat exchangers, and for other mechanical designs that we need to make to improve our productivity in industry on Earth.
Okay. And I think real quick, you said interferomic flow is what is interferomic?
Well, it's a technique using light, and I think it may use laser sensors, laser interferometry, but I'm not 100% sure about that. There's different wavelengths of optical and even sound waves where you can use interferometry, and basically it allows you to make assessments of moving inside of a substance that you can't see visibly. In this case, you can see the motion, as we clearly saw in the video there, of the oil, even though we can't. And if there's oil moving, say at 3 centimeters deep into the oil, we can detect what is the velocity profile all the way through that depth and at various depths, much like MRI can do with imaging our bodies. This interferometry method is using to visualize the flow field all through that concentric annulus of silicon oil.
Okay. And you said these small models, I guess, basically that we're looking at on space station help us understand better what's going on inside of the Earth.
Yes, and also in the atmosphere and in the ocean, or the world ocean circulation and atmospheric circulation on a global scale.
It's interesting, a very interesting way that what the work that we're doing on the space station helps us learn more about the
It
Earth.
is, and that's just one more of the unique applications that the International Space Station offers as a laboratory. Obviously there's no gravity there, or gravity is exactly canceled out by the centrifugal orbiting of the space station. And because of that, we can have this small model of the Earth, and because of the very clever application of this voltage difference between the inner and the outer sphere, we can actually simulate the Earth-centered gravity with this sphere-centered gravity field produced by the voltage difference.
Okay. Well, I think that's just one of several experiments you want to tell us about. What was the next one?
Yeah, that's one in this theme of fluid physics experiments. Obviously, the silicon is the fluid there, but let me just talk a little bit about why we do fluid physics in space. We usually want to either eliminate sedimentation or convection, which are both gravity-driven processes. If we can eliminate one or both of those, we can unmask more subtle flow processes or transport mechanisms.
So sedimentation is, I guess, particles falling to the bottom.
Settle out, much like well, you toss a rock into a lake, it's going to sink to the bottom. That's a gross example of sedimentation, but particles will slowly sink, even if they're just slightly heavier than the water or whatever medium they're in. They will eventually sink to the bottom.
And convection is heat related?
Convection is when hot air rises,
Okay.
or warm fluids rise in the atmosphere, in the ocean, in whatever container of fluid you have. The warmer fluid or warmer gas will rise to the top in a gravity field, but that gravity field doesn't exist or is canceled out completely in the case of the space station lab, And so those transport processes, sedimentation and convection, are eliminated, and we can investigate, explore, and measure the more subtle transport processes, which are on Earth are dominated by convection and sedimentation, and it prevents us from seeing and measuring those more subtle transport processes, which are really important when it comes to optimizing manufacturing methods, for example, for semiconductors and optical crystals on the ground.
Okay. So that's why we do it in space.
That's it. Is exactly right, and it's really at a research at a fundamental level because it's we can talk about the applications that it might have to semiconductor improvements and optical crystals and other types of manufacturing processes, metallurgy, for example. It turns out that surface tension is a many transport processes are driven by surface tension, and surface tension is one of those more subtle transport processes. But on orbit, you can measure it, and it turns out that at a micro level, even in a 1G field on Earth, at the micro scale, that surface tension or those surface tension driven phenomenon come into play and are very important in understanding the dynamics of crystal growth even on Earth. So don't assume that just because we're making these discoveries on the space station, we would have to use them to produce materials on the space station. That would be prohibitively expensive. We can use what we discover on the space station in manufacturing processes on the Earth.
Okay. Well, I think the next one you were going to tell us about was in space.
Yes, in space, I believe Dr. Eric First earlier this week, he's the main principal investigator from the University of Delaware. He talked about this investigation. I'll talk about it a little bit more. Um, in space uses magnetorheological fluids. It has particles in it that when there's a magnetic field around the uh, the vial of fluid that has the magnetic particles in it. The particles themselves are not magnetic when the magnetic field around them is gone. So when when this magnetic field is pulsed at a frequency, say 10 hertz or 15 hertz cycles per second, those particles will self-assemble. Whereas when the magnetic field is turned off, they're either randomly dispersed in orbit or on Earth, they would sink to the bottom. They would sediment out. So here's a case where we're going to space to avoid the sedimentation transport process. And now we can study how these particles self-assemble at the nanoparticle level. It turns out they assemble themselves into structures, and it changes the viscosity of the fluid. And this is
Viscosity is stickiness, basically.
not stickiness, but thickness. If you've
Thickness.
ever changed your motor oil or bought motor oil, when you buy 5W30 or 10W30, that 5 or that 10 or that 30, that's a measure of viscosity. So viscosity is thickness, and the viscosity or the thickness of a fluid is a very important engineering property, a very important design property. If you want a machine or your design to do something, you may depend on the viscosity of the fluid remaining constant, or it actually changes with temperature, and somehow, in most cases, that's an undesirable effect, but we have to live with it because that's how it works in nature. It turns out that though this pulsing magnetic field may be another way to control the viscosity of a fluid, and it's been used for decades in things like seismic damping systems for earthquake prevention of damage to buildings during earthquakes, and also prevention of large amplitude swaying motions in bridges during wind gusts or earthquakes. In that case, also, it's also used as damping in high-end in suspension systems in high-end vehicles and in washing machines for that matter.
Okay. I think, let's see, we've got two more to go. We should probably
Yes, the
move
other
on
two
to the.
experiments are the capillary flow experiment, which Mark Weislocal talked about, I think, just yesterday. In this slide here, you can see the four vials on the right. There's actually a cartoon on the left that shows the cross section. This is called the capillary flow experiment, and this is the interior corner vessel or interior corner flow (ICF) vessel. In this case, you can see the interior corner in that bottom left corner. It's a 50-degree angle corner, and it actually simulates a straw, or a half of a straw, if you can think of it in that abstract term. We're all familiar with how a fluid will literally flow uphill if the straw diameter is small enough. That's the capillary action, hence the name for this experiment. Um, in this case, that corner, the fluid will flow up that corner against gravity. And in the 0G case, it flows quite fast. Within a few seconds of introducing fluid into that interior corner flow, it moves along, and I can't say up because there is no up in space, but it moves along that corner of its own accord due to the adhesion overcoming the forces of cohesion. The adhesion of the fluid towards the surface of the vessel is pulling that fluid along that corner, and it can actually move the fluid from, as you saw in the diagram, as you proceed from the left to the right, the fluid is moving from the bottom of the vessel, or the lower portion, to the upper portion, displacing the bubble, which starts at the top and then ends up at the bottom. So this also is a quite wonderful discovery because it's a bubble pump as well as a liquid pump. First of all, the applications for this in space would be that fluids don't settle to the bottom of a vessel in space. Because there's no gravity, they can spread out. They can become separated into different sections of the volume. So we can use this method to replace mechanical pumps. We can use the capillary flow action, and that's how we're designing fuel tanks for future vehicles, to move the fluid to a desired section of the tank.
Great. So we can hopefully make use of that in the future. I
Yes.
think I'm sorry, just about out of time, so we
Okay.
should run on to the next
Let's quickly
final
talk
experiment.
about the Marangoni experiment. The Marangoni is a fluid transport process which is very subtle and hard to measure on Earth. It turns out that this experiment involves a column of fluid which is several centimeters in diameter and several centimeters high. At one end of that fluid we have a low temperature, as you see on the left, and the other end we have a high temperature. It turns out that the flow is moving from right to left because the surface tension is high on the left, and that's because the temperature is low on the left. This is a very subtle transport process that we can use to improve our designs of optical crystals and semiconductors on the ground if we understand more the dynamics of it. In this particular application of Marangoni, it's called the ultrasonic velocity profile. That's another measurement method to investigate the flow field inside the column of fluid. So for virtually every uh, millimeter of depth into that fluid and across a wide cross section, we know exactly what the velocity profile is at the micro level.
Well, let me wrap up with one last question. With such a range of experiments, are you ever surprised by the things that people come up with, the ways that we can use the space station for unique research?
I am almost every day, and that is one of the neat things about my job, is that I get the chance to learn about just the beauty of science and the nature that surrounds all of us. And it is amazing the ways we are discovering to use the unique properties of the International Space Station as a science laboratory. It's just truly amazing, and I'm very happy to be a part of that.
Well, thanks so much for coming and talking
Thank you,
with us
Brandy.
again. This was Vic Cooley, and congratulations on surpassing the former record and making it to 67 hours of research done on the space station this week.
Thank you very much. We have lots of teams on the ground that are responsible for all that.